You open your freezer and see rock-solid ice cubes, frozen vegetables stiff as bricks, and maybe even ice cream that's turned into concrete. But right there, sitting calmly on the door shelf, is a bottle of cooking oil that looks perfectly fine. Still liquid, no ice, no crystals, no drama. And that tiny everyday detail sparks a surprisingly deep question. It's one of those simple observations we've all made without stopping to think about it. Yet the answer reveals a hidden world of chemistry, molecular behavior, and the quiet rules that govern everything in your kitchen. Why does oil not freeze like water? Let's find out together, right here, on History of Simple Things. To understand why oil behaves so differently, we first need to understand what freezing actually is. Freezing isn't just something getting really cold. It's a phase change, meaning a substance shifts from one state of matter to another. When a liquid freezes, its molecules slow down enough to lock into a structured, repeating arrangement, a solid. Water is especially good at this. As it cools, its molecules form hydrogen bonds, snapping into a neat crystal lattice that becomes ice. This orderly structure is why ice is rigid, and why water freezes at a very specific temperature, 0 degrees Celsius. Freezing, then, isn't just about temperature. It's about how molecules interact, how neatly they can line up, and how easily they can settle into that solid pattern. And this is where oil begins to tell a very different story. Water is often called a strange substance by scientists, and for good reason. Its molecules are tiny, simple, and highly social. Each water molecule has a slight electrical charge that attracts its neighbors, allowing them to link together through hydrogen bonding. When water cools, these bonds organize themselves into a rigid hexagonal structure. That structure takes up more space than liquid water, which is why ice floats. It's also why freezing water is fast and predictable. Put it in the freezer long enough, and it will always solidify the same way. Oil, on the other hand, doesn't have any interest in playing by these rules. Here's the first big reveal. Oil isn't a single simple substance like water. Cooking oils, whether olive, vegetable, or canola, are mixtures of many different fats. Each of those fats has its own molecular shape, size, and behavior. Instead of small uniform molecules, oils are made of long, twisty chains called hydrocarbons. These chains don't line up neatly. Some are straight, some have bends, and others have branches. Trying to freeze oil is like trying to stack a pile of tangled ropes into a perfect grid. It's messy, inefficient, and slow. Because oil is a mixture, there's no single freezing point. Different parts of the oil begin to solidify at different temperatures, which makes the whole process gradual and uneven. Your freezer is cold, but it's not cold enough to freeze most oils completely. While water freezes at 0 degrees Celsius, many cooking oils don't start to solidify until well below that, sometimes at temperatures colder than -20 degrees. Even then, oil doesn't freeze into a solid block. Instead, it becomes cloudy, thick, or slushy as some fats crystallize while others remain liquid. That's why olive oil turns hazy in the fridge, but doesn't become hard like ice. This partial freezing gives the illusion that oil doesn't freeze at all, when in reality, it's just freezing very slowly and very unevenly. Another key factor is shape. The molecules in oil are flexible and asymmetrical. Some have double bonds that create kinks in their structure, preventing them from packing tightly together. Water molecules are small and symmetrical, which makes crystal formation easy. Oil molecules are large and awkward, making crystal formation difficult. The more twisted the molecule, the harder it is for it to settle into a solid arrangement. This is also why saturated fats like butter become solid at room temperature, while unsaturated oils remain liquid. Straight molecules freeze easily, bent ones resist it. This difference isn't just a fun science fact, it has real consequences. It affects how food is stored, cooked, and preserved. It's why oil works as a lubricant in cold environments, why engines need specific oil types for winter, and why frozen foods don't rely on oils to form stable structures. Historically, understanding freezing behavior was crucial for survival. Early humans learned that water could be stored as ice, while oils and fats remained usable in cold weather. This made fats a reliable energy source long before refrigeration existed. In modern times, food scientists carefully design oils with specific freezing behaviors to control texture, shelf life, and flavor. So oil doesn't freeze like water because it's complex, flexible, and chemically diverse. Its molecules don't align easily, its freezing point is much lower, and when it does freeze, it does so gradually instead of all at once. Water is orderly and predictable. Oil is chaotic and stubborn. And that quiet contrast explains why one turns into ice overnight while the other calmly stays liquid, even in the coldest corner of your freezer. It's tempting to think freezing is only about how cold something gets, but temperature alone doesn't guarantee a solid. What really matters is whether molecules can settle into a stable structure once their motion slows down. In oil, even when temperatures drop significantly, molecular motion may decrease, but the molecules still struggle to organize themselves. Instead of snapping into place like water molecules do, oil molecules continue sliding past one another, behaving more like a thick syrup than a solid. This is why oil can remain pourable at temperatures where water has long since frozen, proving that freezing isn't just about cold, it's about cooperation at the molecular level. Simple objects often hide surprisingly deep science, and when we slow down enough to ask why, the answers connect chemistry, history, and everyday life in unexpected ways. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'll be sure to give you an acknowledgement for your contribution. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.